All right. Happy holidays, everybody. This is the kickoff to homework 4, part A. So this situation that we're going to be looking at right now, I'm going to explain on my iPad first and then go into Colaboratory and do all the different parameters we're going to need to be looking at. So this situation, we have two tanks in series where we're concerned with the heights of each. So tank 1 is going to have a height of H1, tank 2, a height of H2. There's a small hole at the bottom of each of these tanks where fluid is leaving. In this case, the fluid leaving from tank 1 is going to be called Q1, and that is equal to the cross-sectional area of that hole times 2GH, the square root of that. And then similarly, we have Q2. The cross-sectional area of the hole is going to be equal in this case. And then the tank also has a cross-sectional area AC that is equal. Tank 1 has a flow rate going in of U1 and another feed of U2. And then tank 2 has this external feed of U3 that is coming in as well as Q1 is pouring into tank 2 from tank 1. To simplify the expression for Q, we're going to separate this part into just calling that alpha. Our value is given in the problem as just 2. So we can say Q1 equals that alpha value times the square root of H1 in this case, and then similarly for Q2, it's just alpha multiplied by the square root of H2. So we need to somehow get a differential equation with respect to the heights, the change in heights. So what that looks like is dH1 dt, and then we want an expression for dH2 dt. To get these, we can do a mass balance. So if we multiply by the cross-sectional area of the tank by this change in height, what we are looking at is the change in what is coming in subtracted from what is leaving. So the flow rates coming in are U1, U2 into tank 1. So we add those. And then Q1 is leaving. And then if we isolate dH1 dt by dividing across by the cross-sectional area of the tank, we are left with this simple expression for dH1 dt. And then similarly, we can look at tank 2. We have two flow rates coming in, Q1 and U3. And then we're subtracting Q2 because that is the flow rate leaving. And then again, divide by the cross-sectional area of the tank. So now that we have these two dynamic expressions, we can go into Colaboratory and code out all of the different parts for homework A. Okay, so we're looking at part A here. So again, we have these two tanks in series that we were looking at. They have this cross-sectional area that is equal. That was AC, that's 2 square meters. We are given that the alpha value for Q1, Q2 is 2. We're given U1, U2, and U3 as 2, 0.5, and 0.4 cubic meters per second, respectively. And then this first part, A1, we want to calculate the initial steady state heights of the levels in the tank. So that is H1, H2 once we reach steady state. So we're going to go into Colaboratory and then paste in the libraries that we'll be needing for this part. And then I'll kind of explain them as we go. So we are given a bunch of information and we want to initialize all of that first. So we can start with our alpha. That is equal to 2. And then just a reminder, alpha is equal to the cross-sectional area of the hole at the bottom of the tank multiplied by 2 times g to the power of 1/2 or the square root. This is in units of, I guess that doesn't really matter. And then we're given the cross-sectional area of the tank AC that is equal to 2 square meters. And then we're given U1, U2, U3. We're gonna make an array. We're gonna use a Jack's NumPy array. Because down the line I'll explain why. So for U1, we're given that it is 2, and then U2 is 0.5, and then 0.4 for U3. So just inputting those values here. This is in units of cubic meters per second. It's a volumetric flow rate. So that's kind of the big information that we're given up front. So now we need to define a sort of function for that will return dH1 dt and dH2 dt. So right hand side, we need a time, height, and the flow rate parameters, and then we have 2 heights and 3 flow rates u. So we're going to unpack that as h1, h2 for h, and then u1, u2, and u3 for u. And then we need to calculate q1 and q2. So q1 is equal to alpha multiplied by the square root of our h1 just being consistent with q1 because that represents the values for tank 1. And then q2 is similar. The only difference is that we're looking at h2. So we have those 2 values, and then we are going to return another array. The first one being for dH1 dt. So that is the flow rates going in subtracted by flow rates going out divided by the cross-sectional area of the tank. So the flow rates going into tank 1 were U1 and U2. So adding and then subtract Q1 because it was the flow rate leaving, divide that by AC, the cross-sectional area of the tank. Now for dH2 dt, that is the flow rates coming in, there were 2, that was Q1 and U3. And we're subtracting out the flow rate leaving, which was Q2. And then divide that by AC. So now that we have that function, we can use the root solver to determine what our sort of H initial array will look like. That will give us the steady state heights for tank 1 and 2. So using the root solver, we're going to call the lambda function to fill in the anonymous variable for H. We're going to call the right hand side function. We're going to input 0 as for time, leave H as H, and then we do have our U initial vector. Our initial guess for H1 and H2, we're just going to put 1 in for each. And then what else? I think that is everything we need there. If we do dot x, that gives us the solution. So this is going to be our vector. So H initial, that is what we are given. So the steady state height for tank 1 is about 1.6 meters, and then the steady state height for tank 2, is 2.1 meters. So now if we go into part A2, we want to linearize the dynamical equations that we just received with respect to the dependent output variables and then the input variables. So with respect to the heights and then with respect to the flow rates. So we're going to use Jax to linearize this. And to do this, we are going to take the Jacobian of each with respect to either height or flow rate. So first, we're going to focus on the Jacobian for the heights. So I'm going to represent that as JH, and then we're going to make this a function. This is going to take the Jacobian of the right-hand side function. We want to, so it needs a sort of index of which parameter we're evaluating with respect to. So the default is 0, meaning it would be looking at the time, but we want to focus on the height. So we need to set that to 1. And then to actually get that Jacobian matrix, we need to put in the 3 parameters. So just 0 for time. We have the initial heights and then the initial flow rates. So if we leave JH, this gives us a 2x2 matrix. This is the Jacobian of the dynamic equations that we get out of this right-hand side equation, and then it is specifically with respect to heights. So if we copy this, we can get a similar situation with respect to the flow rates U. The only thing that we change is this index value to 2, because the indexing starts at 0, so 0, 1, 2. We're looking at that with respect to the flow rates. Just making some minor adjustments here, and then we are given JU, the Jacobian matrix with respect to flow rates. So this is a 2x3 matrix because we have 3 flow rates, and then 2, like with respect to DH1 dt and then DH2 dt. So now that kind of answers our question for this one. We want to obtain a linear time invariant representation of the system. So we're going to create sort of state space model. So a state space model has 4 matrices, A, B, C, and D. A and B we have already, so that is our JH and JU. So this is A, this is B. And then this is specifically saying that we want to isolate H2 as the only observed variable, and that's going to come into play in this C matrix, and then this D matrix is going to be left alone as essentially 0 because we don't want any of the flow rates, because C deals with our A matrix and D deals with the B matrix when we are multiplying out. So what this looks like, if we want to use this, so up here I imported scipy.signal as just sig. So what this looks like, we want a linear time invariant system. So we're importing A, B, C, and D, the 4 state space matrices. So A is JH, B is JU, C is just 0 and 1, meaning this represents what we're multiplying to find H1. So since we want to isolate H2, we leave H1 as 0, and then this one we're multiplying by just 1, so we are left with just H2. And then for the flow rates, we're going to set all 3 of those values to 0. So we do get this continuous state space resolution, and then to transform this state space model into a transfer function, we want that between a transfer function between H2 and U3. We want to find that. So we're going to use this here. And kind of to show you what this looks like, we do need the A, B, C, and D. However, now we do need this index value. Since we isolated H2, we are going to be indexing for U. So that is 2. So we can copy and paste here the A, B, C, and D matrices, and then set the index to 2. And then if you can see, this is returning a numerator and a denominator. So we can split that up into just this. We have 2 different variables to represent that. And then we can see that this is the numerator for the transfer function, and then this is the denominator. So to get this kind of all wrapped up into one, we can make this. So just for nomenclature reasons, H2, U3. So these are with respect to each other, and then this is the transfer function. So sig dot transfer function will set out, or I guess return is what the word I'm looking for, the transfer function with an inputted numerator and denominator. So if we want to see what this looks like, so this is the numerator, this is the denominator of the transfer function in the Laplace domain. So the numerator essentially is 0.5s plus 0.2, and then the denominator is s squared plus 0.74s plus 0.14. So that is our transfer function that we receive. And then this last part, we want to calculate a step response of this linearized model, and then also kind of go back and look at the nonlinear model using solve IVP. So to do the step response, we just do our transfer function dot step, and then we see we're given two arrays. We're given a sort of time array and then a deviation array. So we can split that up like how we did up here. So we're gonna name the time array as just t, and then the deviations for H2, we'll name it that. So there we go. And now we can plot what this would look like. So we can do this from this plotly.subplots, make subplots. That's what that's coming from. And then we're going to add a scatter plot where the x value is the time, and then the y values are these deviations plus the initial height of index 1, meaning for H2. So that looks good. And then we're gonna update the layout. Let's say width of 800, height of 600 pixels, and then gonna update the template to Plotly Bart class favorite. We can go ahead and name this as well. So let's take a look at what this looks like. So this is representing, so the x-axis is time in seconds, because to be consistent with units. So we're going from about 0 to 20 seconds. And then with taking this like step function into consideration, this is the H2. So after we reach steady state, the tank level in tank 2 reaches about a steady state value of around 3.55 meters. So that's kind of everything boiled down for where we're looking for the linear model. So for the nonlinear model, we are looking at solve IVP, which we imported from scipy.integrate. That involves time. So we need to make a time plot separate for that. So we'll call that tplot. And we're going to do numpy.inspace from 0 seconds to 20 seconds, just kind of referencing what this looks like here, and then we'll do 100 points in between. So to do solve IVP, we're going to call the lambda function again, and the anonymous variables in this case are going to be time and height. We're going to call the right-hand side function, so we're going to leave t alone, h alone, and then u initial. However, we're going to add 1 to the U3 value because that will represent the step response. So that looks good. Our t-span is going to be from 0, we'll say 50, a few seconds beyond the time plot. Our initial values for this are simply just h initial. We're going to update the method to be rado, and then we have to say that the dense output needs to be true, so it gives us a continuous function. We're going to store the result of this as res. So if we do res.sol, like dot solution, for this t-plot time, we're given two arrays. This one represents h1, and as you can see, we're not concerned with that at all. It's not changing. We isolated, or we're looking to isolate just h2 and see the effects of that with the step response. So this is h2, so we're going to split this up into h1, h2 equals that. So we stored h2 as that second array. So now we can start plotting. I'm going to just copy and paste most of this. So we're doing a second plot, so fig2. And then we're going to add another scatter plot for this nonlinear. So the x here will be t-plot, and then the y values will be just h2. And then the name for this one will be nonlinear. So as you can see, this is kind of how they match up against each other. The linear model that we got up here, it's the same. However, the nonlinear model gives us a larger height, and it doesn't look like it reaches as much of steady state. However, it does obviously start to. But you can see there is this discrepancy between the two. So that kind of answers all of these questions, A1 through A5. So we can jump into the next video for homework for part B. Thank you.